Good morning, all. So today let's see the topic directional derivative. The last class we learned about partial derivatives, and also you all know about the concept of ordinary differential. Okay, so let's talk about directional derivative. Before that, just review the topics of ordinary differential and the partial derivative concept. Okay. So we know that the ordinary differential is from single variable calculus, or as we would say that it deals with the function f having only one variable. Okay, so let's consider that the function have only one variable, that is x. Then to consider the ordinary differential of it, we just take differential of f with respect to differential of x. What does it mean? It means that here the function, let this be the function f, then the change of the function f is denoted as df, and here the change of x variable x as dx, and the ratio between this is the ordinary differential. Or else we could say like here the function is changing with respect to change in variable x, or the rate of change of function f with respect to change in x. So again I'm telling you the change in x, that is here the change actually happens to x, or we could say that here the function f changes in the direction of x. So actually x is changing here, and we measuring the rate of change of function f according to the change in x. Okay, and what about the differential, that is the partial derivative we learned last class. So here the partial derivative deals with multivariable function, right? And let's consider a function f having multiple variables. I'm just taking two variables x and y. Okay, and it's a partial derivative of f with respect to x and partial derivative of f with respect to y. So partial derivative of f with respect to x is actually means that where the function is changing with respect to x, that is x is changing here, and no changes for y is constant, considered constant here. And also we could say like here the function f is changing in the direction of x, or in the direction of x-axis. Over here, what about the partial derivative of f with respect to y? The function is changing with respect to y, or the variable y is changing here, and we say like the function f changes over the direction of y. So here we discuss about the function changing in the direction of x and in the direction of y. What about if we have to find a function that changes in some other directions, or in some other particular direction? Then we need another concept, that is what we are going to learn today, that is the directional derivative. So it's a multivariable calculus. It is in the multivariable calculus, and it measures the rate of change of a function that changes in a particular direction at a given point. Okay, so we'll see the notations and all of it on the next page. Let me take the next page. Okay, so we denote it as the directional derivative of f over the direction of v. This means that here we are finding the derivative of f in the direction of a vector v. So v is the vector here that denotes the direction of the derivative f. So we denote it as the directional derivative of f with respect to the direction of v, or else we could also write like directional derivative of f in the direction of v. Okay. Okay, so we notated the directional derivative like this or this. Uh, there are also different notations, and these two are the famous among them. So here we measure the directional derivative of f in the direction of v. Okay, and what's the formula to do this is that we just take the gradient of f and dot product it with the direction of v. Okay, why we have taking the gradient f here? So gradient f is actually the differential of f. We know that gradient of f is the differential of f partial derivative of f with respect to x and partial derivative of f with respect to y. It's a vector. So here we have to consider the vector gradient vector of f or the derivative of f, and we need that derivative in the direction of v, so that we just dot product it with the direction of v. So how to find out the direction of v? V is a vector and we need the direction of it. So in order to find the direction, we have to take the unit vector of v. The formula for calculating the unit vector is just consider the vector and divide it with the magnitude of that vector. So it will give you the unit vector, and just take the dot product of the gradient and the unit vector. We will get the directional derivative of that function over the direction of that given particular vector. Okay, so just discuss one question here. We'll take an example and we'll do that. So let's consider that the function f is x e raised to y plus cos of xy. Let this be the function, and we need to find the directional derivative of this function in the direction of vector v, that is 3i negative 4j. Let this be the vector v. Either we could write like this, or we'll write in vector form like this. Okay, we'll just write like this 3 4, then it will be easy to calculate. Okay, this is the direction. We need to find the derivative in the direction of vector v, and a point is also given here at the point at point 2 0. Okay, so we need to find the directional derivative of this function f in the direction of vector v at the point 2 0. Okay, so we just need to find out the gradient of f, and just dot product it with the unit vector of v. Okay, whatever the gradient of f here, the gradient of f is the partial derivative of f with respect to x and partial derivative of f with respect to y. It's a vector. Okay, so here what is the partial derivative of f with respect to x? Here x e raised to y plus cos of xy is the function, and finding its partial derivative with respect to x. So the first part will be here the x partial derivative of x is x1, and e raised to y is e raised to y itself, because no change is happening to y is constant there, and only we need to derivative the variable x. Okay, and what about the derivative of cos? Derivative of cos is negative sine xy, and we need to differential x and y. So the differential of x and y is, the differential of x is only need here, that is 1, and y is constant. So here I just multiply the differential of x y as y. Okay, and the differential of f with respect to y, partial differential of f with respect to y, similarly, that is x and e raised to y should be have to be differentiated here. E raised to y, the differential is of f with respect to y is x is a constant here. So x into e raised to y, the derivative of e raised to y is e raised to y itself, plus cos derivative of cos is negative of sine xy, and the derivative of xy is x, as because the derivative of y there is 1 and x is constant, so the derivative of xy is x. So this is the gradient vector, and we need to apply the point 1 2 there. So the gradient vector del f at the point 2o. 2o is the point, so we have to apply that. So here the gradient vector is e raised to y negative sine xy into y, and and the next is x e raised to y negative x sine of xy. So we need to apply the point 2o here. So whatever applying the point 2o here, so what will be the first term? The first term is we have to apply 0 to y and 2 to x. So e raised to 0 is 1, you know that. Negative y into sine. Y is 0 there, so 0 into sine, 0 into anything is 0. So 1 minus 0. And the next term is x e raised to y. X is 1 there, x is 2 there, and y is 0. So 2 into e raised to 0, that will get into 2, negative 2 into sine xy. So y is 0 there, and whatever sine 0, sine 0, sine 0. So we get the vector as 1, 2. So this is the gradient vector. And what about the unit vector v? So v vector is 3, 4. So we need to find the unit vector of it. So unit vector just divided with the magnitude of the vector. What about the magnitude of the vector? 3, 4, the magnitude is 3 square added to 4 square and its square root. So that is 16 added to 9, we will get 25, and square root of that is 5. So just divide the vector by its magnitude, then we will get the unit vector. So we got the unit vector, and now we just need to dot product to the gradient vector and the unit vector of v. We will get the directional derivative of f. Okay, I think you can do that. We'll wait for a minute. Okay, so the gradient vector dot product v unit vector as the gradient vector we obtained as 1, 2, and just dot product it by 3 by 5 and 4 by 5. The answer we get is 1. 1 multiplied to 3 by 5, we'll get this 3 by 5 itself, and just add it with 2 times of 4 by 5, that is 8 by 5, and the answer is 13 by 5. So this is an example we did to find the directional derivative of the function f at a given point 2o. Okay, and I will give you some more questions as an assignment to work out. So we'll discuss that.